Okay, strap in everybody, because today we're diving headfirst into some seriously mind-bending physics. We're talking about a field so profoundly strange, it feels like something straight out of science fiction.
It's definitely pushing the boundaries of what we thought was possible.
You guys know how much we love to get into the really complex stuff here on the Deep Dive. And this time, we're talking about a field that just might hold the key to unlocking some of the universe's biggest secrets. We're talking about terrestrial, very long baseline, atom interferometry, or TVLBAI for short.
Pitchy, right?
Definitely rolls right off the tongue. But seriously, this stuff is incredible. And our listeners are going to love it because it sounds like something straight out of Star Trek. But before we get ahead of ourselves, let's start with the basics. In a nutshell, imagine a telescope that uses atoms, not light, stretched out over kilometers. This telescope is hunting for the faintest whispers of gravitational waves and maybe even glimpsing the elusive nature of dark matter. Now, I know what you're thinking. Atoms, like the building blocks of matter. Atoms. How can those be used like light in a telescope?
It's all about quantum mechanics, the weird and wonderful world of the very small. In the quantum realm, particles like atoms don't just act like tiny marbles. They can actually behave like waves, too.
So we're not just talking theory here. This wave-particle duality is a fundamental concept of quantum mechanics, and it's been experimentally proven.
Exactly. And just like we can manipulate and measure light waves, we can do the same with these atom waves.
This is where it gets really wild, because there are some pretty mind-blowing theories out there about dark matter particles being incredibly light. I'm talking lighter than anything we've ever directly observed before.
And remember what we said about the wave nature of particles. The lighter the particle, the longer its wavelength. So some of these dark matter candidates could have wavelengths stretching out over kilometers.
Hold on, kilometers?
Yeah.
As in, like, the distance you drive to get groceries.
You got it. We're talking huge EE wavelengths.
Okay, now that's where TVLBAI comes in.
Exactly. We're talking about detectors so big they act like giant particle antennas capable of picking up these incredibly faint signals that have been, until now, completely undetectable.
Okay, so we've got these massive atom telescopes searching for dark matter. But we're also using them to study something else equally mind-blowing: gravitational waves. And everyone listening has at least heard of those, right? They're literally ripples in the fabric of space-time. Einstein himself predicted them over a century ago, and we've been able to detect the crashing cymbal moments of some of the most violent events in the universe, things like black holes or neutron stars colliding.
And we owe a lot of those groundbreaking discoveries to instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory. It's been revolutionary.
Absolutely. But as amazing as LIGO is, it's really only tuned to a specific range of gravitational waves, those high-frequency waves from the very end of these cosmic collisions.
Think about it like listening to a symphony, but you can only hear one note.
We're missing a whole lot of music.
Exactly, and that's where TVLBAI could completely change the game.
So we're talking about black holes spiraling closer and closer together for millions of years before they finally merge. And TVLBAI could be our ticket to hearing that entire cosmic symphony.
You got it.
Now, that's a pretty wild idea. But why does it matter? What would observing those subtle gravitational waves tell us that we don't already know?
It's about pushing the boundaries of our understanding of gravity itself. Imagine being able to see, or rather hear, those ripples propagating over millions of years. It would be like watching a slow-motion replay of the universe's most extreme events.
And not just seeing what happens, but seeing if what we think should happen actually does happen.
Exactly. It would be the ultimate test of Einstein's theory of general relativity.
And maybe even reveal where it breaks down.
Precisely. There's always the possibility of finding something completely unexpected, something that forces us to rethink our understanding of the universe at the most fundamental level.
And then there are the supermassive black holes, those behemoths that lurk at the centers of galaxies. We still don't fully understand how they form, and some scientists believe that studying the mergers of smaller black holes with TVLBAI could hold the key.
It's like trying to understand how a cake is made, but you've only ever seen the finished product. With TVLBAI, we might finally get to see the ingredients and the baking process, so to speak.
We could potentially look back into the universe's history and finally understand how these gravitational giants came to be.
It's a tantalizing possibility. And it's not just about the telescopes themselves. We're also seeing incredible advances in AI that could revolutionize how we analyze all this data.
Okay, so now we're talking AI. This is getting good.
We're on the verge of having more data than we can possibly process with traditional methods. But AI algorithms, they could be the key.
So we're basically giving astronomers a superpowered AI assistant to help them sift through all that data and find those hidden gems.
Exactly. It's like giving them a cosmic noise-canceling headphone set to help them hear the universe's whispers more clearly.
Okay, that is just too cool. While we're on the subject of cosmic mysteries, there's another one that's been keeping scientists up at night for decades. Dark matter.
Ah, yes, the universe's best-kept secret.
We know it's out there, we can see its gravitational effects on galaxies and galaxy clusters, but we still have no idea what it actually is.
It's like trying to understand the contents of a gift box by just shaking it, feeling how heavy it is, but never actually getting to open it and peek inside.
We can see how dark matter interacts with gravity, but it doesn't seem to interact with light the way ordinary matter does, making it incredibly difficult to study.
It's like it's playing a cosmic game of hide and seek, and it's winning. All our usual astronomical tools, telescopes, they all rely on light detection, so they're basically useless when it comes to directly observing dark matter.
Right, and that's what makes this next bit so exciting. TVLBAI might just be the cheat code that lets us finally win this cosmic game of hide and seek.
Now you're getting it. Remember how we talked about those ultralight dark matter particles potentially having wavelengths stretching out over kilometers?
Yeah, it was mind-blowing.
Well, here's where the very long baseline part of TVLBAI comes in. Imagine these kilometer-long detectors acting like giant particle antennas, specifically tuned to pick up the faintest whispers of these particles as they pass through.
Okay, so while other methods are trying to catch dark matter indirectly by its gravitational effects, TVLBAI could be the first to actually catch the particles themselves.
That's the hope. Can you imagine actually being able to study the properties of dark matter directly to finally understand what this mysterious substance is made of?
That would be absolutely revolutionary. It would completely change our understanding of the universe and how it evolved.
It would rewrite physics textbooks, that's for sure.
Okay, so I'm fully on board with the why. This is some seriously next-level science. But what about the how? Building detectors that sensitive that can pick up the faintest whispers of something like a passing dark matter particle. I mean, that has to be unbelievably difficult, right?
Oh, you're absolutely right. We're talking pushing the very limits of atomic physics and engineering.
What kind of challenges are we even talking about? Give me an example.
Well, for starters, you need lasers that are incredibly stable and precise. I'm talking about lasers that can manipulate individual atoms with incredible accuracy, nudging them along those kilometer-long paths without losing track of a single one.
It's like a cosmic game of atomic billiards.
Kind of. And then there's the isolation you need. These atoms have to be isolated from any external vibrations or interference. Even a single stray air molecule could knock an atom off course and ruin the whole experiment.
It's like creating a giant super-sensitive sensory deprivation tank, but for atoms.
Exactly. We're talking about maintaining ultra-high vacuums along those entire baselines, which is no small feat.
So where on earth do you even begin to build something like this? Do they have to build some super secret underground bunker or something? Super secret underground bunker, huh? I mean, it makes sense if you need to be that isolated.
Well, not quite a bunker, but you're on the right track. To get the kind of pristine, quiet environment that TVLBAI needs, scientists are looking at putting these detectors in some pretty unusual places. Deep underground labs.
Deep underground. Seriously.
Yep, seriously. These labs are like oases of stillness, shielded from all the hustle and bustle and vibrations happening up on the surface.
Okay, now that's just cool. And when you think about it, it makes perfect sense. I mean, we're talking about trying to hear the faintest whispers of the universe here. You don't want a truck rumbling by and ruining these experiments, right?
Exactly.
So where are they thinking of building these underground physics labs? Did the CERN workshop material mention anything specific?
Yeah, they actually did. There are some pretty amazing places on the short list. For starters, there's CERN itself, home to the Large Hadron
Of
Collider.
course, CERN. I mean, they've already got these massive tunnels built for particle physics experiments. Might as well get the most out of them, right?
Right. No point in letting good tunnels go to waste. But they've also got their eye on a couple of other intriguing spots. There's Bowlby over in the UK.
Bowlby. What's in Bowlby?
It's actually a working mine, but it also houses a deep underground science lab. And then there's Sanford in the US.
Sanford. Now that name rings a bell.
It's another spot already known for its deep underground research facilities.
Okay, so we've got former mines, we've got these high-tech physics labs. It's amazing to think that these places could be repurposed to explore the universe in such an incredible way.
And here's something even cooler: researchers aren't just looking at existing labs. They're using super sensitive instruments to actually study noise patterns deep underground, trying to find even better locations in the future.
So they're learning to listen to the Earth itself, finding those quietest spots where these experiments can really shine. I love it.
It's like they're searching for the perfect acoustic chamber, but on a planetary scale.
This is why we love doing this show, folks. Who knew that exploring the universe would lead us deep underground? This is what happens when you combine incredible human ingenuity with cutting-edge technology and a good dose of curiosity.
It really is. And that's the beauty of TVLBAI. It's not just about new discoveries, it's about a whole new way of doing physics. If we can figure out how to overcome these technological challenges, and I have a feeling we will, who knows what we might find?
It's like opening a door to a whole new realm of the universe, a realm where the rules of physics, as we know them, might just be rewritten.
And who knows, maybe those ultralight dark matter particles we've been talking about, or those subtle whispers of black hole mergers, those are just the tip of the iceberg.
A tantalizing thought. And there you have it, folks, our deep dive into the mind-blowing world of terrestrial, very long baseline atom interferometry. Make sure to check out our show notes for links to all the research we discussed today, plus some amazing photos of the underground labs vying to host these experiments. And hey, who knows, maybe one day we'll be broadcasting live from a cave somewhere talking about all the amazing things we're learning about the universe from deep beneath the Earth's surface. Until next time, keep looking up. Or should I say, keep looking down. Because sometimes the most incredible discoveries are hidden in the most unexpected places.